Okay, here's a couple more slides on optics from Chapter 2. And here I'll give a summary review of lenses, the thin lens equation, and also imaging with thin lenses. Also show a quick schematic of positive lenses, negative lenses, and cylindrical lenses. Well, basically we know that light is bent or refracted when it hits an interface between media of two different refractive indices. And if we draw a prism here, here this triangle is a prism. It's made out of glass, and if we are careful to trace a ray through this, we could find a ray which goes more or less like I've drawn here. In any case, this ray is bent twice as it hits these two interfaces, and tends to be bent back down and changes direction as it goes through that lens. Well, we can take this concept of the prism and make a continuously changing sort of angle. We can think of the lens as sort of part of that prism, and we can think of a lens as two prisms sort of put together, and look at the behavior of light as it passes through what we're going to call a thin lens. And what we do then is we define an optic axis. Okay, this is a line in space, and we orient our lens perpendicular to that. So the lens is, think of a piece of glass, think of a magnifying glass. And what we'll do is we'll draw some rays, and I'll show you the very basic behavior of the lens. Basically, what a lens does is it brings planar wavefronts, that is parallel rays, to a focus. So I'll draw some rays coming into this lens here. I'll draw one of them called the principal ray going right through the center of the lens. And these rays hit that lens, and then they're all bent to some degree. Actually, the one that goes along the optic axis is not bent, but the others are all bent towards the optic axis in this case, as follows, and they all, at least ideally in the thin lens approximation, hit the optic axis at a single point. So I'm going to draw these rays sort of coming down, going through this point on the optic axis. So this is supposed to be symmetrical. And so what we've said is that we've started with parallel rays. And these rays have been brought to a focus. That is, they converge at the focal point. Of that lens. Rays are brought to a focus. So we say. And we characterize this lens by its focal length, which is this distance between the lens axis and the focal point. Okay, so we have these rays converging to a focal point, and the lens is then characterized by f, the focal length of the lens. Okay, what we can do is we can consider how thin lenses are made, and lenses are made from spherical surfaces. Thin lenses are anyway. And each spherical surface, think of slicing the top off of a basketball or something, has a radius of curvature. And we're going to allow the surfaces of the lens, the front surface to have a radius R1 and the back surface to have a radius R2. And for each radius you can imagine completing the entire circle to help you see that radius. The larger the radius, the flatter the surface. Okay? So here, the back surface has a radius R2 which is larger than R1, and that back surface is a little bit flatter than the front surface. We can write down the thin lens equation for this lens, and that is that 1 over f, the focal length, is n minus 1 where n is the refractive index of the lens, times 1 over R1 plus 1 over R2. Okay, so this is the basic idea here. Note that larger n gives us a smaller focal length. So the higher the index, the smaller the focal length, the more powerful the focusing power of the lens is. We can define the power of the lens. And we also notice that larger R1 and R2 give us larger focal lengths. And in fact, when R1 and R2 both go to infinity, we just have a flat slab of glass, and that flat slab has no focusing power. The parallel rays just go straight through it. They're all parallel. And in that case, we say that the focal length has diverged out to infinity. Okay, so that's the basic equation for a thin lens and its behavior with the focal length. What we'll do here next is look at the basics of forming an image with a lens. And lenses do form images. Think of a magnifying glass. Okay, I'll have fun here and bring a magnifying glass in front. Okay, so here's my magnifying glass because I'm getting old. I need it to see small things. We can use what are called the rules of ray tracing to give us a geometrical construction for image formation. And as I say, I assume this is all review for you, but I'll give you a quick example where we have a thin lens, we have our optic axis, we've notated 2 points on the optic axis, which are distance of the focal length from the lens, and those are called focal points. I'll go back up here and relabel this a focal point of the lens. Okay? And what I'm going to do is I'm going to go ahead and put some sort of an object, and we use an arrow because we can keep track of the orientation of our object this way. I'm going to put an arrow out here, and I'm going to show you the construction of the image of that arrow from this lens. There are 3 rays that we trace. So what we're going to be interested in is we're going to be interested in the rays that come from this point here, where they all converge. Okay? The reason we see something, for instance the point of this pen, is because we can look at it with our eyes and see rays diverging from that point, and they all appear to come from that point. And so what we'll do is we'll take 3 characteristic rays. First of all, we're going to take a ray that comes in parallel to the optic axis, and we know that rays coming in parallel to the optic axis are diverted through the focal point on the optic axis. And so we'll go ahead and trace this ray like this. Another ray, called the principal ray, goes right through the center of the lens, and by symmetry it is not diverted at all. And that's where the thin lens approximation comes in. And so I'll trace this ray going right through like this. And we can see that these 2 rays, which have diverged from this point, have now converged here. There's a third ray, which is just the opposite of the first one, coming in through the focal point on the input, and it will emerge parallel to the optic axis symmetrically. So I'm going to go ahead and draw this ray, which comes in through the focal point, and that ray will emerge parallel to the optic axis, and by golly, it does converge to the other 2 at this point. And that's the basic geometry of image formation. So what we're going to do is we're going to say we've formed an image of that object right here. So we're going to call this our object, and we're going to call this our image. We're going to call this the object distance, and this the image distance. Okay. And we're going to note here that this image is inverted Okay, and so if we define a magnification, the magnification will be less than 1. And we'll also write down the thin lens equation now, which says that 1 over f is 1 over the distance of the object. All these distances are measured from the lenses, plus 1 over the distance to the image. Okay, and so we could solve this for the image distance if we want. It's d object times f over d object minus f. We're going to skip over a lot of details about positive and negative lenses, about sign conventions on these quantities, positives and negative signs, and just deal with this equation as we have it. You guys can do algebra and you can figure out what happens as the signs of these things change. What I will do though is I'll draw a quick picture of what happens with a positive lens. So a positive lens, I'm going to draw my optic axis first. Positive lens has a positive focal length like we've been drawing here. And positive lenses cause rays to converge. Okay, and so I can draw some parallel rays coming in like this, and I can see that these rays are going to converge to the focal point. The other thing that happens with positive lenses when they're thin lenses is that I can have parallel rays coming in at some other angle, like this. I could have parallel rays coming in like this. And what happens is these parallel rays all come to a convergence point, but that convergence point is now off of the optical axis, and in fact it's somewhere in what's called the focal plane of the lens. And that focal plane is located at a distance of f, the focal distance, from the lens. And so these blue parallel rays all come to a focus at this point. They're all bent like this. And we could go through the details applying Snell's law and show that this all works when we use this thin lens approximation. Okay? Now negative lenses are totally different. They have inverted geometry. In other words, they're thinner at the center of the lens than at the end. And based on this construction with the two radii of curvature, mathematically we take their radii of curvature to be negative. Thin lenses will take parallel rays and cause them to diverge, as if they were emanating from a single point back on the same side of the lens. So these rays will diverge according to this construction. And in fact, this point and this distance are the focal length of that lens, and for a negative lens that focal length is less than 0. So positive lens cause rays to converge, and this is also called a divergent lens, where f is less than 0. Okay, so those are the basic equations and the basic ideas of lenses and image formation. Thanks.